Alright then, so let us begin. So this is the naive based numerical that we have here. So it's quite a simple one. Let us begin. Now before we begin, however, I want to point out that this simply will use the naive Bayes method and not the Gaussian naive Bayes, simply because we do not have any continuous values. So if we had values like 3.14, 2.71 or anything like that, anything like 9.8 as well, if you had anything like this, you would have to use Gaussian naive Bayes, right? So that is how that works. But since you do not have any of those continuous values here, it's simple categorical stuff, you can simply use naive Bayes and that's about it. You can be quite very happy. Okay, now before we do this numerical, I'll give a little bit of context here. So naive Bayes simply operates on the Bayes theorem, right? Now what is the Bayes theorem? It is quite simple and quite popular as well, and it's used quite a lot. So it simply states that if you have P A given B, if you want to find this out, it will simply be equal to P of B given A multiplied with P of A divided by P of B. This is what it is. Now usually with naive Bayes we kind of rename some of the labels, I mean only one of them specifically. So the probability of it being class C given X is equal to probability of X being in class C multiplied with probability of C itself divided by probability of X. Now we have certain names for these things as well, like for instance the probability of class given X is itself called the posterior. The probability of X given C is usually called the prior. Probability of X is usually the evidence, and probability of C on its own is likelihood, right? So now these are just some fancy terms. They kind of represent very simple things. We'll take a very simple example and move. So for example, let us say you're interested in making a spam classifier and you're running a certain thing and you're asking, so what is the probability that given the word hello in a mail, it is spam? So you're asking, given that I see the word hello in an email, what is the probability that it is actually a spam email? So how would you do this? It's very simple. So you would write probability of it being a spam email given the word hello is simply equal to the probability of hello in a spam email. That makes sense, multiplied with the probability of spam email on its own, right? So you may not be getting spam emails, or you may be getting a lot of spam emails, whatever it is, you put that there, and the probability of hello in an email at all, right? So that is how it is done, right? So this is basically sort of what is running the whole system, right? And this is what we will use whenever we want to calculate certain things as well. So yeah, this is basically what is going on. Now I could also here maybe talk a little bit about probability not being equal to likelihood, right? They're not the same, they seem very similar, but there is quite a bit of difference. So if I give you a fair coin and I ask you what is the chance of seeing head, what is the probability that you'll see a head, you'll say it is 50%, right? You say 0.5, 50, whatever it is, all the same. But then if I tell you something like this, so again this particular line of reasoning, where if you are given a particular coin and you're asked to tell the probability of getting a particular outcome, that is probability. But then if I ask you a very much more different question, let's say I tell you I had 10 tosses of a coin, I got 7 heads and I got 3 tails. Now I'm not asking you about the probability of heads here, because again that is not necessary. I told you that I did 10 tosses and that I got 7 heads and 3 tails. All the information is out here, but I'm asking you a much more different question, a more meta question. So what is the chance that this coin was biased, and what is the chance that this thing was unbiased, right? Now those are very interesting things to answer, because usually you would expect that a coin would give you like a 50-50 result. So here you would have expected a 5 heads and 5 tails kind of a situation, but you have a 7 heads and 3 tails going on. So it seems like it is biased. So what you are able to do essentially when you are calculating likelihood is you are basically trying to reason about this particular distribution that you have just got, and that is basically what you will try to answer for, if whether this distribution can happen more when it is a biased coin or if it is an unbiased coin. So you will get a certain value and you'll basically compare them and figure it out. That is how that works, right? So that is sort of the small difference that you have here. So it asks a more meta question. It no longer is about probability, it is more about the distribution itself. It is about the underlying distribution. So if the coin is biased, it will give you this kind of a distribution. If it is an unbiased coin, it is supposed to give you a 50-50 distribution. So it is a more meta question, again, as I said earlier. Now yes, so I think that covers, I think, most of the basics. One other thing that I want to sort of point out here is that Naive Bayes, because of the mathematical foundation that it uses, is a very simple and naive algorithm. It is quite simple, right? It is very naive, as its name suggests, right? And now why is that? It assumes that all the features are independent. Right? Now what does that mean? So it means that if it sees the word, like, let's say you my god, you won a lottery, let's say it sees this. Now you as a human, since you have eyes and a brain, you will see this sentence in a mail and you will go, I never registered for a lottery and this is very much a scam, right? You will look at this whole sentence. You're not looking at it word by word. You're looking at a sentence and going, nah, there is no way, this is unlikely, and you will reject it. But what Naive Bayes does is it considers you as a single word, one as a single word, as another word, and lottery as another word. And what it does is it checks your other spam emails that you might have given it as input, and checks where all these words have occurred and if in those mails it was a spam or not. So it does not even care about the ordering. You could literally write lottery won a U. It makes no sense to us, but Naive Bayes will just take that, compare that against the corpus that it has, of spam and non-spam, and then finally give you a verdict. So that is how it works. So you as a human might look at this and be like, no, this is glaringly obvious, it is 90% a spam, for example. Naive Bayes might look at this and go, maybe 70%, maybe, it's not very sure. So even though this thing might be glaringly obvious to you, the system will be like, I'm not really sure, it might or might not be. So sometimes it does not perform well, but generally actually it is a pretty good algorithm. It works pretty well. It is quite very powerful, right? But yes, it just assumes that things are independent, and therefore sometimes it misses the very obvious things. So that is a drawback, but yeah, generally it is a pretty good algorithm. Now here they've asked us to classify this particular target data, so red SUV domestic, and they have given a training data set, and they're asking us if this particular target data thing will be stolen or not. That is basically it. Now if it wasn't clear already, where is my mouse? Yeah, there it is. If it wasn't clear already, this is the target, right? So or the target class, whatever it is. So we have two classes here, which is yes and no. So we have to just tell if the particular car thing is going to be stolen or not stolen. Very simple, very nice, very easy. Now we will keep this very straightforward. We are not going to calculate unnecessary things. We'll only calculate things with respect to whatever is required here. Okay, so let's move. So the very first question that we must ask here is basically what is the distribution of the targets themselves, right? So what is that distribution? So that is what is the probability of yes and what is the probability of no, right? First we have to know that, because there is only two classes and we are kind of going from a top-down approach. So we want to understand what is the probability of overall distribution in a sense, right? So we'll notice here that there's how many. First we'll see how many total entries there are. So we have 1 2 3 4 5 6 7 8 9 and 10. So we have a total of 10 entries. That's quite informative. Now how many of them were actually stolen? 1 2 3 4 5. That's very nice. So we have an even split of stolen versus not stolen. That's very nice. Great. So we have this. Now let us go ahead and calculate some conditional probability. Conditional probability, the prior information basically, right? So we will calculate that. Now we have to calculate this for both yes and we also have to do it for no. The reasoning is quite simple. Now when you calculate this naive based stuff here, what actually ends up happening is you don't actually get a probabilistic thing. So generally you must be used to things like, you know, if a coin toss occur, like let's say something happens and the probability of event X occurring is, let's say, 0.8, then you can say that the probability of event Y occurring is 1 minus P of X, and therefore it is going to be 0.2. See, you can't do that stuff here, right? Because it just does not follow that kind of linearity, right? So we have to find the values for each class individually through calculation. That is just the way it works. It is, however, quite very simple, because again, it's jolly good, it's very easy, there's nothing that complex going on really. So let us focus on what our target is. So the first thing that we care about is the color, red. Okay, so there's two things that are possible with red color, right? So what is the probability that a red car is stolen? What is the probability that a red car is not stolen? These are not going to be, you know, they're not going to be unit sum kind of a thing, right? Again, as I already said, they are not going to follow that necessarily. They may follow it, they may not follow it, but again, it's not a strict rule here. So let's look at the data points. So yes, red, so we just have to care about those things first. So that's 1, that is 2, this is yellow, so we don't care, yellow, so we don't care, 3. So there are 3 cars that were red and that were stolen, and we already know that 5 cars were stolen overall. So we have a 3 by 5 going on. Now let's look at the cars that were red but were not stolen. So this was red but it was not stolen, so that is 1. Then this was red but it was not stolen, so that is 2. That is very cool. So we have 2 cars that were red that were not stolen, right? So out of the 5 cars that are not stolen, 2 of them were red. Very nice, very informative. Let's keep moving. Next we have an SUV type. Okay, so now we simply have to find out the same thing again. So we have to find the probability of it being an SUV and being stolen, and then we have to find the probability of it being an SUV and not being stolen. Very nice. So SUV, here we go. So you have 1 SUV that was stolen, and that's it, literally. Okay, that's great, amazing work. Now how many SUVs were not stolen? Let's look at that. So 1, 2, 3. There we go. So that's 3 by 5. So that's 3 by 5. Now again, notice here that it's quite obvious, right? 1 by 5, 3 by 5, they don't actually sum up to a 1. And that is why I said that they don't necessarily follow that unit sum rule. That's just how they rock. Now we have the next feature, which is domestic. Again, we repeat the same old thing again. Domestic being stolen, then the probability of domestic not being stolen. Very nice and very easy. So domestic. So 1, 2, and that's it. Only 2 domestic cars were stolen. So we will have 2 out of 5 here. The domestic cars not being stolen. No, 1, 2, 3. Okay, that's great. So I have a 3 here. Great, we are done with everything now. So we have all the data that we could ever ask for in order to perform our calculation, right? It's very simple now. So now we do the final posterior calculation. So the value for yes, basically overall, is going to be the probability of the car being stolen first. So it has to be stolen, right? So that is the chance that we'll consider. Then the probability of the car being red and being stolen. The probability, whoops, that is flipped, probability of an SUV being stolen, multiply the probability of domestic being stolen. So what does that sort of multiply, or how does that come out to be? So probability of yes is of course 1 by 2, and then let's look at these 3, 1, 2. So we have a 3 by 5, 1 by 5, and a 2 by 5, which very simply turns out to be a 6 by, I'm not really going to calculate anything here, I'm just going to write it like this. This is what it is. Okay, we'll move on. So this is the value. Then the value of no, is going to be, we can just, I'll write the equation first. So first of all, the car should not be stolen. So what is the probability of the car not being stolen? Multiply with the probability of a red not being stolen, multiply with the probability of an SUV not being stolen, multiplied with the probability of domestic not being stolen, right? Given that it was so probability that probability that it is domestic, given that it was not stolen. Basically, that is what it is. I'm using shorthand here, sort of saying whatever I want, but I think it is quite very understood what I mean. Now red no, so you have 2 3 3, so we can just write that 2 by 5, 3 by 5, 3 by 5. Now you can of course go ahead and do calculation here, but I think what can be very easily understood here is that if you compare them, right, so value of yes and value of no, you will notice that you have, with yes you have 6 by 5 cube times 2, and with no you have 18 5 cube 2, by whatever it is. So you can get rid of the denominator and you will notice that no has 3 times more chance of happening, basically, right? So we can say that the value of no is much greater than value of yes, therefore the car won't be stolen. That's it. It's literally that simple. So you look at the data, you look at all the information you have, you run a very simple probability based check, and that is simply how you perform this whole thing. It is quite very simple and elegant, and that's about it. The craziness only really happens when you go for Gaussian naive Bayes, but then again the whole process is quite simple if you have the formula. That's about it. So yeah.